Okay. Hi, everybody. We got a thinned out crowd later in the summer. Hopefully, a couple other people roll in. Let's get started. So, couple announcements. First one is extra credit. So we do this at the end of Data 100 every time, but you can get a half point of extra credit, half percentage point for filling out the course evaluation. And that includes both the official course evaluation that Berkeley puts out, and then also our own internal survey that Data 100 does, which has been significantly shortened compared to previous semesters. So it shouldn't take you that long. But the questions that are on there are really important. That's why we ask them. So to the extent that you can spend some time giving your feedback about the course, that's really, really useful to us. And if 90% of the class can reach the threshold where they've finished both of these surveys, then we'll give an extra half percentage point to everybody who filled out the survey. So you can get up to a percentage point of extra credit in Data 100 this way. Really shouldn't take you too long. The links are in the slides. We'll send out an ed post as well with those links. Okay, announcements. We're getting to the end here. Exciting. B1 is due tonight. B1 is tonight. Lab 11's tomorrow. B2 is due Monday. You got your final next week on either Wednesday, Thursday, or Friday. We're wrapping up. You're almost there. Tomorrow's guest lecture is going to feature Ben Packer, who's a very accomplished data scientist who's done work in industry at Google and the fairness team there. He worked at a company called OPower that got acquired by Oracle. If you get a utility bill, you might see OPower on there. They like revolutionized how things are happening in utilities, and now works at a nonprofit called Recidiviz that helps get people. It just makes the criminal justice system more efficient and fair. Kind of wins for both sides of the criminal justice system. So anyway, come chat. Ben's going to be talking about lots of projects he's working on, and then also what sort of the environment is right now for getting hired as a data scientist, which I know is something that everybody tends to find pretty valuable who's in Data 100. Because I'm curious too, what hiring sort of looks like. Not going to be recording, not going to be live streamed. If you want to talk to Ben, if you want to see Ben, got to be here in person. You all are already here in person that I'm looking at, so hopefully you can come tomorrow, learn something from Ben. I'll be here as well. Michael will be here as well. We'll hopefully wrap up a little early and Ben can take individual questions up front. We'll also try to have like a Q&A session with the big group. Okay, so tomorrow should be a lot of fun. A little different than what we usually do for the last lecture in Data 100. Okay, final exam. Everybody has now been assigned a slot to take the exam or been told when you're going to be taking the exam. Okay, Wednesday, Thursday, or Friday of next week. If you can't make your assigned slot and you know that information now, you need to tell us. You need to tell us, please fill out that final exam emergency form and we can see what we can do. If you tell us the day of or the night before, it's not guaranteed that we can accommodate your request. Okay? There's my event tomorrow that if you RSVP'd for, great. The final exam sort of prep proctored session. So hope to see you there. If you RSVP'd, you can check out Ed for that. We're also going to have an exam prep and final review with Sammy on Friday from 2 to 4, and you're welcome to hang out in Warren 101B past 4 o'clock. Good opportunity to get a bunch of studying in. And then I decided on Monday and Tuesday of next week during lecture time in this room, I'll do exam office hours. So I'll take any question that people have, and you can see me struggle with the practice problems up here for you all. I'm not going to live stream it or record it, so if you want to come in person. As long as we have this room, we'll use it. Okay, so feel free to just come next week as though you're going to regular lecture, and we'll talk all about the exam. Okay, and then when people don't have questions, I can fill it with my own stuff. Okay, roadmap for today. So we're going to be talking about clustering today. Clustering, a type of machine learning algorithm. I'd say this is probably the easiest of the lectures sort of in the second half of the course. That doesn't mean it's the least interesting of the second half. If anything, I think it's a super, super interesting topic that you probably haven't been exposed to before. So it's a very visual topic too. If you got a pen and pencil, recommend you take it out. Okay, so quick taxonomy of machine learning, just to remind you of what we've been learning about so far. So Michael's been taking you through a lot of this, but in machine learning, if we have labeled data, if we have outcomes, I've got a new iPad today, so we'll see how it does. If we have outcomes, okay, our outcomes can be quantitative, they can be numeric, or they can be a category. We perform what are called regression and classification. if we have outcomes, if we have some outcome for each observation, right? The person's income, right? Whether or not they succeeded at something, there's an outcome that we can sort of say whether it's correct or incorrect, our prediction. But, and this is called supervised learning, just to go through this again, it's creating some function that maps in outputs. You're trying to map these pairs, you have these x's, and you're trying to predict some y, right? You have some input set of features, input vector, which we call features, output values, which we call labels, or all I call outcomes, okay? We have these things called regression, we have these things called classification. These are all words you should know coming out of Data 100. When someone talks about a regression algorithm or a classification algorithm, you should know what they're talking about. That's supervised learning, that's what we spend the most time on in Data 100. Unsupervised learning we spend less time on in Data 100, but it's still a very important machine learning topic and really deep machine learning topic. You already learned a bit about unsupervised learning. You learned about dimensionality reduction in PCA with Michael in the last 2 lectures. Notoriously tough lectures. If they were tough, that's good. You're learning PCA. Today we're going to talk about clustering, another form of unsupervised learning where, again, we don't have labels for our data. There is no outcome. There is no correct cluster. We're trying to identify patterns in the data without knowing what's sort of correct. This is a different style problem. A different style problem. Okay, so let me give you an example of clustering in the real world. So here's just one, but image compression. Image compression. So why do we have to compress images? When you open like a JPEG on your computer, that's not the original image that was taken by your camera. It's some compressed image. It takes up less storage space. Images take up a lot of storage, especially raw images of sort of just the world as it is. Everything gets compressed. And so when you can reduce the number of colors used in a particular image, okay, you can reduce the storage size, and then our eyes often can't even see the difference. Okay, and so how could you do this with clustering? Let me give you an example here. So let's say you had a grayscale image that had 6 different colors in it. These are the 6 colors. This isn't the actual image, but let's say it just had 6 colors. Now, these 2 colors are pretty similar, I would say. These 2 colors are pretty similar, and these 2 colors are pretty similar. If I were to take the average of those colors, right, those have like a grayscale value between like 0 and 256. If I were to take the average of those 2 colors, I get 3 new average colors. And let's say I replace all of the instances of those 2 colors in my picture with that new average color. I'd find some average of each of those groups, and I'm going to replace the color with the centroid of each cluster. I'm calling these now a cluster of colors. The centroid is just the average, the middle, the center of those clusters. We're going to hear these words today. And so I'm just going to replace each pixel with its cluster centroid or its cluster center. Okay, now you might ask, how did I pick 3 colors here? How did I decide to do 3? Just sort of convenient. We're going to see later. You pick K. You pick the number of clusters. That's coming in a little bit. But if we do this, you can see this is Professor Nargis Narouzi's cat, Pishi. On the left, we have the original image. It's kind of a fast-moving GIF here, but you can see when the clusters jumps to a really low number like now, the image becomes much less clear, but it's very compressed. It's much, much smaller than it was before, but we can still make out that it's still a picture of a cat. Okay, so this is just one example of clustering in a very sort of simple setting. This is one thing clustering can be used for. You can use it in social networks to identify clusters of people. You can use it in mapping, like weather patterns, all different kinds of things that clustering is very useful for. This is just one of them. So just to quickly go over what sort of clustering approaches are out there, I want to give you a hierarchy of clustering approaches. So there are literally hierarchical approaches to clustering. That's going to be the second half of today's lecture. Hierarchical approaches to clustering. And then we have these partitional approaches that sort of split our data into distinct pieces, one layer of distinct pieces. And hierarchical approaches to clustering, there are these different approaches to merging together clusters. We're going to talk about all 3 of these today: single link, average link, and complete link clustering. On the partitional side, there's lots of different approaches to clustering. We're only going to look at one today. We're going to talk about k-means clustering, distinct from k-nearest neighbors, which you learned about in Data 8. We're going to talk about k-means clustering, but there's other algorithms out there. For example, like expectation maximization, the E&M algorithm. That's a very useful algorithm for clustering and trying to identify the distributions that actually created your underlying data. Okay, but critically, the idea here is that in hierarchical approaches, we're grouping data into nested clusters, kind of like Russian dolls that go into one another. We're going to see this in a bit. Hierarchical clustering starts with every single data point as its own cluster and builds up so that all of the data is just one giant cluster and sort of fills in the gaps in between. It's pretty cool. Whereas the partitional approaches on the right don't do that. They try to identify a distinct set of clusters, just one layer of clusters. Okay, it's more computationally efficient than the hierarchical approaches. Hierarchical approaches are usually more appropriate for smaller data sets, whereas these partitional approaches are typically more useful in larger data sets. Hierarchical approaches can be very slow in small data sets. But that's sort of the extent to which I'll tell you when these two things are sort of used differently. I recommend reading offline if you want to learn a lot more about clustering. It's a deep, deep world and super interesting. And like I said, we're just going to talk about single average and complete link hierarchical approaches, but we're going to start with k-means, which is very fun to teach. So is hierarchical clustering, because it's all very visual. I'm going to be drawing lots of pictures here. That's why I'm happy we have the new iPad today. So the annotation should be nice and smooth. So let's talk about k-means clustering. K-means clustering. So I'll give it to you in text first, and then we'll actually draw the picture. This is sort of the canonical, most popular clustering algorithm. If you want to cluster something, if you tell somebody what is the clustering algorithm that you know, k-means is the first one, almost guaranteed. This is like what people know, and it's like a good place to start. How do you do it? So you first pick an arbitrary k. You might ask, how do I pick a k value? That's coming. We're going to talk in a bit about how to pick k. K is the number of centers, the number of clusters that you want in your picture. So if I want 3 clusters, k equals 3. 5 clusters, k equals 5. Okay? So we're going to pick a k, and then we're going to repeat this following process that's pretty simple until it converges, until it stops. So what do we do? The first thing you're going to do is you're going to color the points according to their closest center. So we have some data set. We're going to randomly place some points, color the points according to their closest center, and then we're going to move those centers, those centroids, to the center of all of the points with that same color. And then we're going to rinse and repeat. And this is essentially guaranteed to converge, except in some really weird cases that don't really ever happen, this will converge. Let me give it to you as a picture, because it's much easier to see it in a picture. Here's some raw data with just x and y values here. Okay? It's very common in clustering to take really high dimensional data, bring it down to 2 dimensions so you can see it like this. What would be a useful technique for taking data from a lot of dimensions to just 2 dimensions? PCA. PCA followed by clustering is a very common approach. Very common approach. That's why we teach it first. Okay, so here's some raw data for you. How many clusters are in this picture? 2. Like we look at this, we can kind of see 2. Maybe you're like, maybe we could split the thing on the right into 2 clusters, so we'd have 3 total. Okay, there's a lot of subjectivity in clustering. Okay, so we're going to initially place some 2 centers. So what do I do here? I'm going to randomly place 2 centers within the range of the data. Notice the center isn't up here. That's beyond all the y values here. It's within the range of the data. So I randomly place 2 centers, literally random. Okay, you might ask, does this algorithm depend on the initialization of those centers? Yes, it does. You can get a different output. We'll see that in a bit. But we have 2 centers. Step 1, we've initially randomly placed 2 centers. Why did I pick 2? We're going to talk about that in a bit. For now, just go with it. Okay, these are often called centroids. What do we do then? We color the points according to their closest center. We're going to color the points according to their closest center. So all of these points, their closest center is that top left star. The other points, the closest center is the star on the right. Not so bad. Okay, computationally, you have to go through and like figure out all these distances, but not so bad to start with. Okay, what do we do from here? We're going to move the centers, those randomly placed centers, to the average of their assigned colors. So I'm going to actually take those centers and literally move them to the average of those 2 groups. How do you take an average in multiple dimensions? Average of the x's, average of the y's, that's your new point. Right? We're going to move our centers to their new home. So notice the centers have now moved. What do we do next? Rinse and repeat. I'm going to recolor according to their closest center. This isn't necessarily going to be exactly the same set of points colored exactly the same way as before. Now that we've moved the center, there might be some new colorings going on. So notice now all of these points are colored according to the bottom left center, and the orange and blue are obviously here, just arbitrary colors here. And all of these points are now colored orange. What do we do next? Exactly the same thing. Move to the new center. In this case, we don't move as far. We don't move as far. Notice we're getting, looks sort of like we're approaching some sort of local optimum here. So we're going to move our centers. We're going to recolor, move our centers, except in one step this time. Recolor, move our centers just a little bit. Recolor, move our centers just a little bit. Notice they're starting to sort of land in the same spot. Okay, I'll go through this one more time just so you can see this approach. Once you see it once, it becomes very clear. Randomly assign our centers, move them to the mean of their assigned points, and iterate. Assign, move. Assign, move, assign, move. Keep going until convergence. So notice between iteration 4 and 5 here, between iteration 4 and 5, the assignment of points to colors did not change. The assignment of points to colors did not change. Notice all of these points are assigned to blue, and the same set of points are assigned to orange. There wasn't a change between iteration 4 and 5 in terms of assignment. Once this happens once, and the points no longer are getting assigned to a new color, you've reached convergence. Okay, except in some really, really strange, odd edge cases, essentially k-means clustering always converges. I like to put that asterisk because there's technically some weird cases where it can land in this oscillating point. Never happens. Okay, so between iterations 4 and 5, the centers moved slightly, but the assignment of points did not change. At that point, k-means, we say, has converged. It has converged to a solution, and this is essentially guaranteed, except in some really weird edge cases. Feel free to read that link if you want to read about it. This really will never happen to you. Okay? That's k-means. That's literally it. There's improvements to k-means that have come out, an algorithm called k-means plus plus. It just takes this k-means algorithm and puts some modifications on it, so it runs a little bit faster, it has better guarantees, but ultimately this is like still used. Okay, this is a good thing to understand. Okay, so now one thing I want to note, k-means is different than k-nearest neighbors. These are very often confused, and for good reason. They both start with a capital K. Okay, k-nearest neighbors works like this. K-nearest neighbors is a classification or regression algorithm. Really, you just want to think k-nearest neighbors is supervised, right? K-nearest neighbors is supervised, whereas k-means clustering is an unsupervised method. It's an unsupervised method. Okay, k-means is used to cluster points. There's no outcomes. There were no correct clusters in the picture we just saw. If anything, you might look at those clusters and say, those look kind of incorrect to me. Why is that little straggler point being classified for the bottom left cluster? Right? We can tell and sort of look at this and say, that doesn't really quite look correct, but according to k-means, that's correct. That's weird. So we'll talk about that a bit. Okay. Again, there isn't really anything in common with these two different algorithms. Just know they're sort of distinct algorithms. Okay, now, how do we know if a clustering is good? How does k-means know if a clustering is good? I want to talk about something called inertia, which you may recognize from physics. So let's say we did k equals 4 here. Let's say we picked k equals 4 clusters. If we run k-means, we could end up with this clustering, okay? We see these 4 clusters. You might say that doesn't really look like 4 or 3 separate clusters in the top right. I would agree with you. Okay, but we've run it with 4 clusters. That's the output k-means gives us. If we rerun it multiple times, in this case we're using different random seeds, we get different assignments. We end up with different results. We have k equals 4 clusters, but notice, depending on that initial placement of those centroids, we might get a different result with k-means. Okay, so it's good to run it several different times anytime you run it in the real world and see which one performs best. But what does it mean to perform best? How do we say something quantitative about performing best? So let me ask you, which of those 3 performs best just visually? And let's see if we can translate that into a formula. And don't worry about thinking too hard here. Which one of those looks best? It might be easier to see on your phone. Slido working? Yeah, good. Okay. Oh, I never handed these out. Sorry. I'll just hand it to the next guy. Yeah. All right, take one, pass it down if you like. Take two if you like. Not that many people here. Take three, I won't even know. All right, throw in an answer here. Which of these clusters looks best? Which one of these sets of clusters looks best to you? Okay, we have pretty solid agreement here. Pretty solid agreement that A looks best. And let's take a look. So to do this quantitatively, we need to define some sort of loss function. We need to define what best means. We need to come up with some sort of loss function for clustering. What does it mean for a cluster to be good? So it looks like most folks said the leftmost cluster, like of these three, looks pretty clean, right? I'd say the middle one looks not bad either. I'd say the left and right ones are, in a lot of ways pretty equivalent. The one on the right, though, is definitely a little funky. It's got this big split in points. But the one in the middle, one on the left, not so bad. But how do we actually quantify this somehow? So what does it mean for a cluster to be a really good cluster? If you're really insular, you want your cluster to be really tight, right? And you want it to be far away from other clusters. You want them to be very distinct, and you want them to be very tight. So let's start with the tight piece. What does it mean for a cluster to be very tight? So a tight cluster is one that has a small sum of squared distances from the center to each of the data points. That's inertia. That's inertia, the sum of squared distances from each data point to its center. Distortion is the same thing but weighted. Let me show this visually. Again, visualization, very helpful with the clustering lecture. So in this case, we just have 2 clusters and 7 data points. Cluster at the top right, there's some center. The center has some distance to each one of its points. If we just add up those squared distances, same thing here, add up those square distances, that's the inertia. Okay, if we have tight clusters, inertia is going to be small. If we have really wide clusters, inertia is going to be larger. You might see another metric called distortion out there. We're not going to talk about it a lot in Data 100. Distortion is just the weighted sum of squared distances from each center to its data points. Why is it weighted this way? The idea is that it's weighted so that each cluster is valued the same. Okay, each cluster has equal weight. So what do we do to make sure each cluster has equal weight? Divide by the number of data points in each cluster. Notice I'm adding up the inertia for the cluster on the left. Oh, sorry, I circled these incorrectly. Sorry, that might have been a little bit confusing. We have, this cluster first, and then this cluster over here. But notice now, we're dividing by 3 and dividing by 4. All this is doing is weighting our inertia so that each cluster has the same weight. Okay, so if you had one really tight cluster and one really not very tight cluster, your distortion's going to be large, but your inertia might be small. Okay, so we're weighting them equally so that we want every cluster to be good. But we're going to focus on inertia. So if you look at the inertia statistic for each of these different clusterings, you can see that the inertia is smallest in the far left. It's a little bit bigger in the middle. The 2 on the left, pretty close to one another. But the inertia on the far right is substantially larger. Why is it so much bigger? Well, you have this really big error between that centroid and its assigned points. You can see this middle cluster is quite a bit wider than it is in the 2 clusterings on the left. Okay, we just have more spread out clusters in the far right. So now we have a way to actually express when a clustering is good for a particular k. Notice in this case we have k equals 4. We've run k-means clustering several times. We now have an idea of how to pick which clustering is best within that set. How do you pick k? We still haven't addressed that. But I have a mystery for you. What is the inertia when k is the number of data points? Feel free to talk with your neighbor on this. What is the inertia when k equals your number of data points? In the previous Example, k was 4. What is inertia when k is your number of data points? Assuming every point is assigned to a cluster. Okay, let's see. So assuming every point is assigned to its own cluster, if k equals n, let's say every single point gets its own cluster, okay, what ends up happening? So I'll give you an example. If k equals the number of data points, then every data point ends up becoming its own cluster. That's the most efficient way to assign every point to a cluster. Why is that? The distance from every point to its cluster center is 0. So if I have 3 data points, and I put the cluster centers right on top of those data points, the distance from each data point to its cluster center is 0. The sum of square distances is also 0. So inertia is 0. This is the equivalent of fitting a super high degree polynomial that touches every single data point in unsupervised learning. There's such thing as overfitting in unsupervised learning. This is a nice example of overfitting, an analogy to overfitting. So the question is, how do you avoid this? How do you pick a value of k between one giant cluster, and n clusters that's optimal? We're going to get to that in a bit. But for now, I just want to ask you a question. For a single value of k, we saw before we had a single value of k. We had k equals 4. K equals 4. I gave you 3 different clusterings. Right? Let me just show you a picture. Okay, this is just 3 possibilities. What's the absolute best way to cluster all of these points? What's the absolute possible lowest inertia that you could get from all of these points? So as it turns out, this is actually a very hard problem to go figure out where to put your 4 cluster centers to minimize inertia globally. This is actually a very, very hard problem. So how would you do this brute force? Well, you could go say, well, there's 4 different ways to color each point. 4 different ways to color each point. So there's 4 options per point, and there's n points. So there's 4 to the n colorings. If your data set has 10,000 data points, 4 to the 10,000th power is really, really big. That is not a number your computer can handle very easily, if at all. 4 to the n. Okay, so what do you have to do for each of those 4 to the n colorings? You have to go figure out what the centers are, and then you have to compute the inertia, and then you have to compare across all 4 to the n different colorings which one is best. And as it turns out, there's no better way to do this than the brute force. Brute force is literally the best way to do that. There has not been an algorithm that's been found to do this better, to find this minimum more optimally. And this isn't something you have to know for data 100, but as it turns out, k-means is part of this special class of problems that are NP hard. K-means clustering is finding a locally optimal clustering. It is not finding a globally optimal clustering. Globally optimal clustering is essentially impossible to find in a reasonable amount of time for a data set that's not too small, right? For a very small data set, maybe not so big of a deal, okay? For a giant data set, you can't find a globally optimal clustering. So how do you get around this? You fit it, just like gradient descent, when you run it multiple times. You run k-mean several times, you pick the best. You see what kind of variation you get, and you hope that that's good enough. Okay? Okay. Which clustering do you like better? We have the one on the left and the one on the right. Keep in mind the one on the right is what we got earlier. We got this way earlier in the lecture when k equals 2 for that same data set. K equals 2 gives us the clustering on the right, and then there's also this clustering on the left. Which of these two do you like better? Which of those two do you like better? Hopefully this is a quick one. I like B. It's nice to be different. Let's see. So we look at these two clusterings. Okay, good. There's some people who agree with me. They like B. They like B, but A is really like the clustering here, right? This is the correct clustering almost objectively when we look at this. The problem is K-means lands on the clustering on the right. The inertia is substantially lower for the clustering on the right side. The clustering has a substantially lower inertia. Why is that inertia lower? Well, if you look at this little data point here that was colored blue, if we assign it to the cluster in the top right, where as humans we look at this and say it should be assigned to, the distance between that point, and its sort of correctly assigned cluster is actually longer than the distance between that assigned point and the cluster that's clearly distinct. And so it has lower inertia. K-means the algorithm ends up choosing the clustering on the right here, even though we disagree. So in the second half of the lecture, we'll talk about how do we actually cluster in a way where we correctly get the cluster on the left. So why don't we take a couple minute stretch break? We'll come back. If folks have individual questions, feel free to raise your hand. Any clarifications about k-means clustering for the big group? Questions about k-means? Making sense? Big step in your data science journey to learn k-means clustering. You now know an unsupervised method that you can explain in one page, right? PCA, a little trickier, also unsupervised, still useful. K-means, a little bit simpler. Okay, let's go ahead and keep going here and talk about another form of clustering. Hierarchical agglomerative clustering. I saw a lot of heads go up. Hierarchical agglomerative clustering is a really scary word for something that's pretty simple, okay? That's like one thing, good lesson in data science. Don't be afraid of something till you know what it is. Hierarchical agglomerative clustering is this big word for an incredibly intuitive process. In a lot of ways, hierarchical agglomerative clustering if you had to sit down and actually go figure out how to cluster data points on your own, and you sort of thought about it for a couple hours, I wouldn't be surprised if a lot of you ended up landing on agglomerative clustering as your method for forming clusters, because it's just so darn intuitive. Okay? Essentially, all you do is start with every data point separately, and then just sort of glob them together. So the two closest data points get merged. The next two closest data points get merged. Keep going. Then you start dealing with clusters of data points. The closest two clusters get merged. Closest two clusters get merged. And you keep doing this until you just end up with one giant cluster. That's it. That is literally hierarchical agglomerative clustering in two data points, or two bullet points, excuse me. Okay? So you start with every data point separately, and then you just glob up one step at a time. Now, if we're globbing up individual data points, you can imagine that if we have a really gigantic data set, this is going to take forever. Okay? And indeed, hierarchical clustering is more useful on smaller data sets where you sort of want to understand what happens between every separate data point all the way up to one giant cluster, whereas k-means is a little bit more computationally cheap, a little bit easier to use on these larger data sets. Again, I recommend reading about clustering offline if you're sort of interested in when you would use each method. In Data 100, we don't focus on that distinction too much. Okay? So this is called a bottom-up or agglomerative method. The linkage criterion determines how we're going to combine clusters. So I said we're going to merge the closest points together. What does closest mean? What does closest mean? That's the big question. Closest is exactly what this linkage criterion is. What is the definition of closest? So let's do this. Some linkage criterion. So the simplest linkage criterion is the single linkage. Single linkage. Single linkage says the first merge that you should make, or the next merge that you should make, the sort of primary one that's going to happen, is the two clusters or two data points that have the minimum distance between each other. The minimum distance between each other. What do I mean by this? Let's try this out. 8 data points. This one you can just draw right out. How do we do hierarchical clustering? We're going to merge the two data points that are closest to one another. Okay, if there's a tie, we'll just break it randomly. So what do we do? 1, 2, 3, 4. So we have 4 to start. Now is where it gets trickier. Now is where it gets trickier. So now we're going to start merging clusters based on the minimum distance between any 2 points in different clusters. So these 2 clusters on the left, what is the closest possible distance? Closest possible distance is the distance from this point to the distance to that point, or equivalently, the other one. What's the shortest distance between the top 2 clusters? The shortest possible distance is between those 2 points. Which of those is shorter? The one on top. We're going to merge the top and bottom clusters next because they're equivalent to one another. Following me so far? Not so bad. Very intuitive. Then what do we do? Well, we have 2 clusters left, so merge them. And we have one giant cluster. Notice what we end up getting is actually a history of different clusters. A history of different clusterings. Hierarchical clustering comes up a lot in genetics because you can look at genes, see how they relate to one another, and actually form histories for those genes and do a lot of very interesting things in genetics. We're going to see a picture of something called a dendrogram in just a second. Okay, average linkage is instead of using the minimum possible distance between 2 points like we did, you're going to use the average distance. Not the distance between the averages, 2 different things, the average distance. You're going to compute every pairwise distance between every single cluster. With a lot of data points, that's pretty expensive. Every single pairwise distance between every point in every cluster. That's a lot of points. Simple operation, but that's a lot of points to do it on. That's average linkage. Complete linkage is sort of the hardest of the 3 conceptually, but it's exactly the same as what we did on the left, except instead of using the minimum distance to determine which are closest, we're going to use the maximum possible distance between any 2 clusters. So how do we do complete linkage? To start, the points just get merged. All of the closest points we can see look something like this. The next step is the trickiest. The next step is the trickiest. So what we want to do now is find the maximum possible distance between points in any two clusters. So if we look at the clusters on the left side, what's the maximum possible distance between any 2 points? Well, it's going to be the distance between this point and this point, or the other side of that x. And in the top, the largest distance is going to be the distance between the two outermost points. So instead of using the shortest possible distance, the best case, complete linkage uses the worst case to measure distance. The worst case to measure distances. And in this case, on the left, that maximum distance is shorter than the distance up top. So notice we find the maximum worst case distance between each cluster, and then we use the minimum of those maximum distances, just like we did on the left. So we end up merging them top to bottom, and then what do we do with our final two clusters? We merge the whole thing. Okay, so notice we end up in the same spot. We started in the same place, but we got there a little bit differently. Single linkage versus complete linkage. I'm going to pause for a moment. Questions about single linkage versus complete linkage. We're going to do a more complicated example of complete linkage in a sec. But questions about complete versus single linkage here. One way to remember this, single linkage is sort of what you would naturally do. Best case scenario, shortest distance between clusters. Complete linkage, worst case scenario. What's the longest possible distance you could measure between clusters? Average linkage, what's the average? Okay, nothing crazy. Like I said, hierarchical agglomerative clustering sounds terrifying, but it's not that bad at all. Okay, keep going. Let's do a complete linkage with a lot more data in a non-trivial set of data. This is a real data set, okay? Where we have 12 data points here. So 12 data points, we start off with 12 different clusters. And so let's do this sort of with pairs. So I recommend finding somebody else. I'm going to give you some distances to start. I'm only going to show you 3 distances at a time here. So notice, it might be a little tricky to distinguish the lines here, but we've got this red distance between 10 and 11 is 0.14. This orange distance right here is 0.22. And this gray distance here is also 0.22. So which 2 points do we merge first? 10 and 11. Okay, so we're going to merge 10 and 11. Those 2 points become a cluster. Okay, go ahead, talk with your neighbor. What gets merged next here? What's going to get merged next here? Talk with your neighbor here. What's next? So we're looking for the shortest distance. I'm only giving you 2 significant digits here, so there's really no way to tell. If you assume that my ordering in the top left is top bottom, or smallest to biggest, then 0 are going to get next, and 5 are going to get merged after that. Okay, so we got 0 to 4, and 1 and 5. Okay, 1 and 5 are also going to get merged here. But then things start getting trickier after this point. Starting off, it's pretty easy, and there's algorithms that'll do this for you under the hood, right? But you want to understand what's going on. So 1 and 5 are going to get merged next. But then the question becomes, well, what's closest here? 6 and 8, 7 and 9, or 0 and 3? We've now reached our first sort of cluster difference. We're not just looking at distance between points. So if we're doing single linkage, then the distance between 0 and 3, cluster 0 and point 3, single linkage would be this distance. That's single linkage. Okay? Single linkage is the shortest possible distance. Complete linkage is the longest possible distance. And then average linkage would be the average of those 2 different values. If there were more than 2 points in the cluster, it would be average of all of the distances between the point in the cluster. Does that make sense visually, the difference between complete linkage here and single linkage? Best case versus worst case. Okay? And so if you look, it's a little hard to tell just looking, inspecting here, but 6 and 8 are closer, and 7 and 9 are closer than either of those points in 0 are to 3, or at least the longer one. So what do we do next? We're going to go ahead and merge 7 and 9. Okay, we're going to merge 7 and 9, and we're also going to merge 6 and 8. So notice what's going on here. 7 and 9 have a distance of 0.3. That's here. 6 and 8 have a distance of 0.32. That's here. For complete linkage, again, worst case scenario, the distance between cluster 0 and 0.3 is 0.36. So that's going to be third after all of those merges take place. Make it sense? So we're going to merge, what are we doing? 7 and 9, and then 6 and 8, and then 0 and 3. Okay, and then 0 and 3. So now let's merge 0 and 3. Okay, what else do we have sort of competing here? This was 0 and 3 from before. That's that distance. What's next? So we start looking at our clusters. The one in the bottom left, easy to forget. Those look pretty close to one another, and indeed they are pretty close. They're just a little bit longer than the distance between 0 and 3 were. The distance between cluster 1 and cluster 10 is 0.41, so those are going to get merged next. Whoop. Those are going to get merged next, 1 and 10 in the bottom left. Now what do we have? Now what do we have? Well, we also have now the distance between cluster 0 and cluster 7. That's 1.17. That's here. And the distance between 0 and 6, very close, but a second place here. 0 and 6 is 1.2. So we're going to merge 0 and 7. It's very nice and visual here. Merge 0 and 7. Hopefully you're seeing the pattern here. We're going to merge now 0 and 6. Those are the shortest. What do we do next? We have one cluster in the bottom left, one cluster in the middle, single point up top. The shortest distance here is the distance between that middle cluster and the top right point. Those two are going to get merged. Two giant clusters. The last step is easy. You just merge everything. Okay? Once you go through this a couple times on your own, it becomes very easy. I recommend taking a look at these slides, going back and doing step by step through this entire process. The first time I saw this image with all the lines connecting, it seemed like a lot. Ultimately, we're just connecting groups of points that have the shortest distance from one another. Okay, where we define shortest distance in a different way depending on the linkage criterion. Best case, worst case, average. Questions about any of the merging steps that happened here? Questions about any of those merging steps? Donald, go ahead. Yeah, so let me explain that one more time because that's a good confusing, good point of confusion here. So what we're doing when we do hierarchical clustering, if we go all the way to the beginning, is we're going to start with every data point as its own cluster, and then we're merging the most similar clusters. Another way of saying that is merging the clusters that are closest to one another. Okay, the clusters are closest or most similar to one another. The question is, how do you define how close two clusters are to one another? How do you define how close two clusters are? There's multiple ways to define two clusters being close to one another. You could say that the distance between clusters is the minimum possible distance between any 2 points in those clusters. So let's say we had clusters that looked like this. What does it mean for us to say how far are those clusters from each other? Well, one way to measure that distance is to say that's the distance between the two clusters. The best possible case, take any 2 points in the two clusters, measure the shortest distance. Or we could say, well, what's the worst possible case? Take the 2 points that are farthest away from each other in those two clusters. If we define distance in the top way, that's called single linkage. The best possible case, the bottom is called complete linkage. Once we've established the distances between all the different clusters using that linkage criterion, Then we say merge the two closest that are most similar, the clusters that are closest to one another according to this measurement. So there is something weird going on where we might say find the minimum distance, find the maximum distance, find the average distance. That measures the actual distances between the clusters. Then we go say pick the two clusters that are closest to one another. So there's always this step at the end that says find the ones that are most similar. Okay, it's sort of a two-step process. We can talk more in office hours. That might be a good move. Yes, Isabella. Good. So when you fit hierarchical clustering, you usually do the whole thing. But we'll see in a minute, you might want to pick K at some point, right? We're going to talk about picking K. We're going to talk about cutting a dendrogram. That's coming. Good foresight. What else? What else? Oh, so you're saying instead of finding the average of every single pairwise distance, just use the distance between the average of the points like this. Yeah, it's like, oh, average of different features. Yeah, and so we're doing everything here in 2 dimensions, right, to measure our distances, but this could technically be in many, many different dimensions. And there's many, many different distance metrices that are out there. So for example, there's something called like Mahalanobis distance that like you might use. And so sure, you could use that as a distance metric, but like the commonly used ones are single linkage, complete linkage. Like I said, I recommend reading a lot about clustering offline because there's just like deep literature of clustering that I'm not even familiar with because it just goes like very, very far. It's just not my area of expertise in that way. Yeah. What else? These are all great. Yes. Good question. You have to come up with a tiebreaker criterion. So you might just randomly break ties, right? Randomly break ties. What else? Okay. All right, let's keep going just to make sure we wrap on time here. So we did all this clustering. I recommend taking a look at these slides. The most important thing is to understand what single versus complete linkage, the difference between those two things is. You'll see that all over past exams. That's the thing we really want you to take away from hierarchical clustering is what it is and this idea of using different metrics to measure distance. Okay, so here's like the big payoff here. Agglomerative clustering gets our clustering correct. Agglomerative clustering leads to the clustering that we wanted from the very beginning, where the orange points are all in the bottom left and the blue points are in the top right. Okay. I like to think of hierarchical clustering almost as like infecting the points with each other. It's like spreading an infection on your plot, and eventually you sort of grab all of the points that are near you, whereas k-means is trying to find these like sort of more globally representative spheres in your data set. Okay? That's something, if you read more about k-means, it's looking for these like spherical clusters. If your clusters aren't spherical, k-means doesn't do a very good job. So let's say your data looked like this, okay, where you had like a bullseye pattern. K-means can't handle that data. K-means would split the bullseye right down the middle. Agglomerative clustering could handle that. Agglomerative clustering could actually make that separate clustering going around the edge and handle the cluster in the middle. Okay, so depending on your clustering method, it might be able to handle different shapes. And there's trade-offs between handling complexity and how long it takes to run. Okay, the most sort of popular clustering algorithm that works really well that you can go read about if you want is called dbScan. dbScan, it was introduced a while ago and it's still very, very popular. But we won't test that in Data 100. Okay, so what's so cool about agglomerative clustering too is you get this history of clustering. You get these nice histories, right? There's a tree that you could use to describe the history of all the different clusters that were formed. So if we had a bunch of different genes and we performed PCA on this genetics data set, each gene is now represented by 2 data points, we could go cluster those genes. You can go cluster those genes and think about how they're related to one another. So you might see things like this in the wild. On the right, we have this hybrid dendrogram heat map. On the left, we have just a dendrogram. We'll talk about in a couple slides how to read a dendrogram. But the idea is we get this full history of all of the merging that happened with our data points. Okay, all the way from individual data points at the very bottom, all the way up to one giant cluster at the very top. Okay, sort of reading from the bottom to the top that way. And then the y-axis represents something we'll talk about in just a little bit. But you might see these in the wild. You might see these out there, this sort of heat map clustering, especially if you do like genetics work. Comes up a lot there. Okay, Picking K, this is like what I've been avoiding for the entire lecture here. How do we actually pick K? How do we actually pick K? Okay, Isabella asked for hierarchical clustering. Is there any point where we would stop at a certain number of clusterings? That's picking K in the case of hierarchical clustering. Earlier in K-means clustering, we chose a value of K ahead of time. How do we pick that value of K? What's the best value of K? Picking K is subjective, is my first lesson for you. Picking K is often a subjective process. If you're looking for exact answers, not the best place to find them. Okay, how do we pick K? Look at the clustering on the left here. We have a principal component for each state in the United States, including DC. Don't worry about where those principal components came from. But if you look at that plot, how many clusters are there? I mean, looks like there's kind of one there, kind of one there. You know, are these a cluster? Is this a cluster? Should we do something with something in the middle here, right? Are there no clusters here? It's subjective. The correct number of clusters is not always this easy question. So how do you actually go choose how many clusters you should have? I'm going to give you a couple different methods. Here's one. Okay, one approach. Oh, nope, I don't want to record. Okay, for k-means, one approach is to plot inertia versus many different values of k. So you actually just go test out k-means many different times. So what do I mean by this? What do I mean by this? So let's say k equals 1. I'm actually going to run k-means clustering, okay, with k equals 1. Maybe I'll run it several times. And what I'll do is report the average of the inertia. I'm going to run k-means several times and report the average of the inertia. Let's do it again. I'm going to run k-means with k equals 2 clusters. I'm going to do it several times, just like we saw before. Several times. Find the average of that inertia or the best case of that inertia, whatever. Okay. Plot that. And I'm going to keep doing this, running the k-means algorithm at least once for each of these values of k, and I end up getting a plot that goes all the way to 0. Right? What happens when we have k equaling our number of data points? Inertia is 0. Every point is its own cluster. We can send inertia arbitrarily to 0, just like training error. Just like training error, we can send it essentially as low as we want. In the case of k-means, we can literally send it to 0 if we want. Okay? So what do we do? How do we pick k? Well, our idea here is that we don't want k to be too big. That's overfitting. We don't want k to be too small. That's underfitting. So what does it mean to fit well? So let's go ahead and pick a value of k where we get a big drop. We get a lot of bang for our buck. Okay? And if we were to choose an additional cluster, if we were to increase k by 1, we don't get that much reduction in inertia. So if we look at this plot, what do we see here? So for example, at k equals 3, here's a picture of what k equals 3 looks like. We have 3 clusters in that data set we saw earlier. Notice when we went from one giant cluster to 2 clusters, something like this, we got this big drop in inertia. Clustering was good. That first step does better than just one giant cluster. When we go from 2 clusters to 3 clusters, we get a little drop as well. Still a pretty solid drop. And then after that, more clusters doesn't really improve our inertia. And this plot ends up kind of looking like an elbow. And you want to pick sort of the crook of that elbow. The crook of that elbow. Okay? Your next question might be, well, what if there isn't a clear crook to that elbow and it's just a curved line? And the answer is yes. That can happen all the time. Elbow method only works in some cases. Okay, this is a good place to start. Okay, but it's not perfect. It's not perfect. Data often lacks an elbow. Data often lacks an elbow. It doesn't mean you shouldn't use it. You should definitely plot it. Okay, people will look for this if you're in an interview and they ask you, how do you identify distinct groups of customers? And you're like, well, I could use a clustering method. And then they say, well, how many clusters should you make? Having this in your back pocket is a good idea. Running this analysis at the job is probably a good idea. So then what's like a more robust way to do this? What's a more robust way to do this than the elbow method? So I'm going to give you a couple. So here's hierarchical clustering now. Here's hierarchical clustering. So let's learn how to read a dendrogram. A dendrogram, something we saw before. So at the bottom of our dendrogram are our individual data points. Okay, so these are data points down here. These are data points. Okay, notice we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data points. You might have 10 genes, or 100 genes, or 1,000 genes, right? If you had 10,000 genes, this would be kind of tricky to draw, right? Hierarchical clustering makes more sense with smaller data sets. So what we do in hierarchical clustering is we start merging those points, right? We merge them, and we merge them according to a distance metric. A distance metric. So whatever distance the 2 points were when they got merged gets put on the y-axis. So notice the y-axis here has some value of distance. Sorry, it's small font here. That value of distance is the distance between those 2 points when they got merged. Distance between those points when they got merged. Same idea, and then it just becomes the distances between clusters when they were merged. The distance between clusters when they were merged. So depending on whether you used single linkage or complete linkage, the heights that things get merged can look a little bit different, right? And so eventually, as we sequentially merge clusters and points, we end up in a place at the very top where this distance represents the distance between those final 2 clusters before they got merged. Before the final 2 clusters got merged, that's the very top of the dendrogram, right? And then you could like technically draw a little thing like this, but it wouldn't really mean anything. Doesn't provide any additional information. Okay, and once you have one giant cluster, there's no distance between a cluster, right, in itself. Okay, so that's a dendrogram. How do we actually use a dendrogram? That's how we read it. How do we now use a dendrogram to pick k? Going back to Isabella's question, how do we actually choose at what point we should stop in our history? How do we stop in our history? Same idea as the elbow method. Same exact idea, and same problem you can run into with the elbow method. So start with the data points at the bottom. When 2 points are merged, they're sort of binned in the dendrogram. Y-axis represents the points between the clusters, so we sort of build our dendrogram from the bottom up. And then we sort of choose k by looking top down. So what we do to pick k is we're going to cut our dendrogram at the point of diminishing returns, which again is subjective. So notice when we go from one giant cluster to 2 clusters, right? We only have 2 clusters here. When we went from one giant cluster to 2 clusters, the splits after that had much shorter distances. That first split made 2 pretty distinct clusters. That distance dropped quite a lot compared to the next merge that's going to happen. So how do we choose the value of k? Well, why don't you just go pick the point in this dendrogram where you start getting diminishing returns, where merging 2 points isn't all that useful because they're already so close to one another. And if you were to pick a point here, again, it's subjective. You could argue that really all of these gaps are so small that only this first giant jump really matters. And in that case, you would say, pick 2. Pick 2 clusters. If I were to cut this dendrogram along there, it intersects 2 vertical lines, and I would say, pick 2 clusters. You could also make the argument that really we get diminishing returns after 2 additional jumps, right? These last 2 distances are so tiny that those distinct clusters really don't make any sense. Those points should stay clustered with one another. We shouldn't make them separate data points. And in that case, you might say, like the red dashed line, which I'm just going to redraw right here, if we were to cut our dendrogram at that point, we would have 4 different clusters. So it's very similar to the elbow method. We're just trying to find the point of diminishing returns. At what point does increasing k no longer make a very big difference? So that's how you do it for a dendrogram. You might ask, what if all the jumps are the same size? My answer again would be yes, that can happen, and then this method doesn't work. And so then what's a more sort of robust quantitative method for doing this? We use something called a silhouette score. Okay, last sort of concept for today, the silhouette score. So what is a silhouette score? So I want to give you a measure of something, of a point being very well clustered. I asked this in the very beginning. What does it mean for a point to be really well clustered? You tell me, what does it mean for a point to be really well clustered? What are some things that you would want for a point that was really well clustered? How would you describe a good clustering? Any ideas? What does it mean? Generically. Yeah, go ahead, Martin. Small distance to center. So a good cluster means that a point is close to its center, so it's compact. What else? Brian. Yeah. So the cluster is tight. This is good. So it's like close to the center, low inertia, and then also it's tight. All of the points are sort of close to each other, so it's very low inertia. Good. So we want our clusters to be tight. What else? Yes, in the back. Good. Far from other clusters. We want our cluster to be very distinct. If we have really two tight clusters that are right next to each other, they probably should have been clustered. Right? We want our clusters to be far away from one another. We so far have only addressed one of those points. We've only addressed making our clusters really tight with inertia. We have not talked about this idea of making sure our clusters are very distinct from one another. So the silhouette score tries to encapsulate both of these ideas. The silhouette score is trying to give you a combined measure of compactness and distinction. Compactness and distinction. And so you might imagine that this point on the edge here is a low score because it's sort of far away from its center. It's not very compact in its cluster, and it's also pretty close to this other cluster. Whereas the point that's sort of densely packed in the middle of that upper right cluster, close to its center, right? And it's pretty far away from the orange cluster. So we can say qualitatively, low score point, high score point. How do we actually calculate this? How do we actually give a computation that represents that difference? So we use something called the silhouette score, or the silhouette coefficient, or the silhouette width. If you hear the word silhouette, this is what it's referring to. So high score points, close to their own cluster center, far from points in other clusters. Low score points are far away from other points in their own cluster. Okay? They're kind of like the black sheep of their cluster, right? It's like the person who's sort of different than the rest of their group, and they're totally, ready to like leave and go to another group. A low score point is like ready to jump ship in its cluster. Okay? Low score point, ready to jump ship. High score point, very deeply embedded. Okay? So how do we actually compute this? Every data point gets its own silhouette score. Every data point gets its own silhouette score. What are the silhouette scores? Start with A. A is the average distance to the points in your own cluster, not just the distance to your centroid, not just the distance to your centroid. It's the average distance from you to every other point in your cluster. Okay? The average distance to every other point in your cluster. Call B the average distance to the points in the nearest cluster. How do you define what the nearest cluster is? You need to give a criterion for that. Which centroid is closest to you? So the nearest cluster is in the bottom left. Once we've identified the closest cluster, go compute the average of all of the distance to the points in the nearest cluster. Okay, a lot of computations for each point. Every point has to be compared to every other point. To have a high silhouette score, we want A to be small, we want tight clusters, and we want B to be small. We want B to be big. We want to be distinct. Tight and distinct. A, we want to be small. Points to your own cluster, you want to be really tight. Points to other clusters, you want to be further away. So how do we represent this in an expression? The silhouette score S is B minus A over the maximum of A and B, which most of the time, the larger value of A and B is going to be B. Essentially, this formula is B minus A over B. Most of the time when you compute this, it's B minus A over B if you've run a clustering algorithm. Okay, but we write B minus A over the max of A and B. That's the silhouette score. Every single point has a silhouette score. So you might see this subscripted with an I. Silhouette score, subscript I. Okay, what's the highest possible value of a silhouette score? Give this a go. Feel free to talk with your neighbor. Think about edge cases. If you got questions, raise your hand. I can come by. Keep thinking here. Edge cases. Worst case, best case. What is the best possible clustering? Okay, get that answer in. Let's see. Go ahead. Okay. 1. How do we get 1? Where does this come from? What's going on? So for every data point, we're going to compute the average distance to points in the same cluster. Average distance to points in the same cluster. So let's say we're dealing with this little red point in the top right here. Red point in the top right. B is the average distance to points in the nearest cluster. So if you were to draw B on this picture, it would be approximately the distance between that point and the center of the other points, approximately, because this cluster is tight on the right. Keep in mind the distance between a point and the average of a bunch of other points is different than the average distance to every single point. Two different distinct phrases there. So how do we make S really large? To make S really large, we want a large value of B. Large value of B. So let's go ahead and make the clusters as far away from each other as we can. So B is just like some large positive number. But then how else do we make S really large? We need to make A small. How small can A be? What's the smallest possible value of A? Well, if we want A to be really small, the cluster should be really tight. What's the tightest possible cluster? It's like a black hole cluster. What is it going to be? It's going to be a point and potentially a bunch of other points sitting right on top of one another. And so the average distance to that point and every other point in that cluster is just 0. It's so tight, every single point is just sitting on top of one another. And so A would be 0 in this case. If A is 0 and B is some positive number, the silhouette score is B minus 0 over B, which is just 1. So the best possible silhouette score is 1. Okay, it'd be pretty weird to have a cluster with just a bunch of points stacked on top of one another. So a silhouette score of exactly 1 is like a little funky, but that's sort of our goal. That's our goal for a large silhouette score. So now we actually have a quantitative measure of clusteriness. How good our cluster is. What does it mean for a point to be well clustered? We can use the silhouette score. It's not just inertia. We now can take into account distance to other clusters as well. Distinction, compaction, right? Or tightness. Okay. Can the silhouette score be negative? Can the silhouette score be negative? Is that possible based on this definition? Go ahead, throw an answer in. Okay, can the silhouette score be negative? Good split. I like a good split. So it's weird if it's negative, but it can be negative. It's not unusual. It's just strange. It's not good for a point to have a negative silhouette score, but it happens. So in fact, that low score point on the left, that low score point on the left side of this plot here has a negative silhouette score. Has a negative silhouette score. Why is that? That low score point is closer on average to the points in another cluster. It's closer on average to points in another cluster. B is smaller than A. B is smaller than A. B minus A is going to be negative. So indeed, that low score point actually has a negative silhouette score of negative 0.13. So you have this really like long cluster in this case. These values on the edge are not clustered very well. And this matches our intuition. So the silhouette score can be negative. It can be negative. Okay, so last part of today is reading these plots, these silhouette score plots. A little tricky to read at first. Once you see how they're read, again, not that bad. Theme of a lot of my lectures, I hope. So let's see. So what is this silhouette plot on the right? The silhouette plot separately plots for each of your clusters. So you run some clustering algorithm. You're going to make a separate chunk, okay, a separate chunk for each of your data sets. What you're going to do is just plot in order. Notice the left here is just cluster label. It's just an arbitrary label of the data points, just ordering of their silhouette scores. You're going to plot on the x-axis the silhouette scores across all of the data points. So notice that low score point that had a negative silhouette score is here. What I'm going to just do is work my way through all of the points in the blue cluster and plot all of their silhouette scores. So I'm sort of going to work from the outer edges in, right? Outer edges in, because these points are so well clustered in here. And I'm going to plot all of those values of the silhouette score all the way up to the maximum possible value of the silhouette score of all of the points in the blue cluster. Okay, start with the lowest, work my way up to the highest, and then just shade it in. That's it. So it ends up looking kind of like this fin, right? I'm going to do the same thing for the other cluster, for the orange cluster. Okay, there's just a gap here so it's easier to read. Notice for the orange cluster, all the silhouette scores are pretty high. And based on our intuition, looking at that picture, that looks like a pretty clustery cluster to me. It's pretty well clustered, yeah? Tight, far away from other clusters, yes? So what do we see? All the silhouette scores are really high. All the silhouette scores are pretty high. So we can see that the orange cluster is more clustery than the blue cluster, looking at the size of its silhouette scores. And then what we also typically will throw in the silhouette plot is the average silhouette score across all points. How well are all of our points clustered? How well are all of our points clustered? And you can just produce the silhouette plot across multiple values of k. Pick the k with the lowest silhouette score. Or excuse me, the highest silhouette score, right? If we look at this for another value of k, here's k equals 2, here's k equals 3. We saw at the very beginning of today, our big mystery, how many clusters are in this picture. We saw that there should be 2, and the silhouette score agrees with you now. The silhouette score agrees with you. If we make one of these silhouette plots in both of these cases, we can see that the average silhouette score for k equals 2 is higher than it is for when k equals 3, suggesting that on average, points are more well clustered with k equals 2. So now you have something that's a little bit more quantitative. Instead of the elbow method, where you have to sort of subjectively pick out the elbow, now you might get a silhouette score that actually has like a maximum minimum, right? You might get this like thing that you can actually optimize now. A little bit more clear. Okay, that's the silhouette score. But to sort of just wrap up at the end here with our last minute, ultimately, and somebody asked a question about this on the break that was really nice, it's like, ultimately what you care about is an industry making money, right? And so how do you choose k? You want to pick the k that makes you the most money or satisfies whatever goal you're trying to achieve. Okay, so even if k equals 2 has a higher silhouette score, if k equals 3 nets you more profit, go with k equals 3. Right? Again, as the data scientist, you need to be the sort of subjective overlord to all of this and use these tools for your own benefit. Don't just blindly listen to these tools. A large language model can do that for you, right? So there's like a simple example here. Let's say you're trying to produce t-shirts and you're trying to figure out what sizes to make. I was blessed with a long torso, so I like tall medium shirts, which are very specific and not all companies can make, okay? So we might want to perform 2 different clusterings as the company. Maybe we can cluster all of our customer heights and weights based on a sample from earlier in the class, right? With k equals 3 to small, medium, and large shirts, whereas another company can do k equals 5 and have small, medium, large, and extra small and extra large. And some other great company can also make medium, tall shirts for me. Pick whatever value of k gets you the most profit. If you're not going to sell enough extra small and extra large shirts, and you're not going to get sued for not selling extra small and extra large shirts, don't sell them. Right? Pick the one that maximizes profit. So ultimately, keep that in mind. What is your real world metric for making your decisions? All of the metrics we learn about in the class, right? You want to use them to your advantage along any metric that actually means something to you in the real world. Okay? All right, that's clustering. Tomorrow we have our guest lecture. Please come tomorrow in person. Ben's going to be very, very interesting. So see you tomorrow. Thanks, everybody.